Greetings. This is our video number 19 dealing with proportional injection. Now, behind me, if you take a look at the screen behind my headshot here, this is a shot, the picture I took of a proportional injection system down in the Santa Maria area. Must have been 30 years ago. In other words, this idea of injecting chemicals in a certain ratio that keeps up with the flow rate of the irrigation system. As the flow rate changes, the injection rate changes appropriately. It's not a new concept. It's been around for a long time. Nevertheless, it's not commonly done except for some things like acid, where there's a sensor and they maintain an acid concentration. Some people do that, but most people are still not into the proportional injection. There are a number of companies that are selling proportional systems now, and there are some companies that supply the whole kit and caboodle. In other words, they will go out and set up a proportional injector, and then they give you the fertilization requirements and dosages, and they'll even control it from their office. It's sort of like paying for an accountant, you know. They take care of that part of the work. But nevertheless, it's even though that's widespread in some small areas, it's not widespread, you know, throughout the world of fertigation. If you've been following this video series and trying to learn from it, you know that the books are available on our website. And of our 22 or so videos, they include both lectures and laboratory demonstrations. Proportional, I'm going to drop to the bottom bullet here, proportional injection. Proportional means two slightly different things. One is that the injection rate can change by 10% if the irrigation rate changes by 10%. That's one idea. It doesn't necessarily mean that you're monitoring the chemical concentration in the water. It just says your injection rate changes by 10%. The second thing that we look at is we take a look at how things are changing. In other words, you take a look at the irrigation rate, and maybe you also look at the irrigation water quality changing. And this is more like pH, where the water quality coming in may change over time, but your flow rate may not. And so you have to automatically adjust the rate of acid injection to compensate for the changing pH of the incoming irrigation water. Now I'll go to the top here. Usually, once you have all this equipment in place, it usually means that you're spoon feeding small amounts of fertilizers as they're needed. You're not just occasionally doing something. You know, the idea is you're doing this all the time while you're irrigating. So needless to say, if you're doing it all the time, you're spoon feeding in the mix that you need. It also means that you have multiple injectors that simultaneously inject small dosages of all the different chemicals. So you have multiple injectors, you have multiple injection points. It's really getting kind of to the top of the line here with chemigation. And then hopefully you're thinking a little bit more ahead of time in terms of, you know, all the chemistry and everything like that. Next thing is that proportional always means it's automatic. Now, what's that mean? Somehow you have a sensor without any human interaction. Definitely there'll be a sensor from the flow meter of the irrigation system. But there also might be a sensor, there might or there might not be a sensor somehow on the chemical injection rate itself, or maybe water quality like a pH sensor. But now you're generally dealing with some type of a little microprocessor, and then there are fancy ones and simple ones. It depends on what you're really doing. Although we do have sensors that can be inserted into irrigation pipelines that measure the EC, in other words, the salinity, or else the pH. We don't really have affordable field sensors that we can just plumb in and easily and repeatedly measure fertilizers themselves, like potassium and phosphorus and or phosphate and nitrate. So what it means is that when we do proportional irrigation, we have to first calibrate the injectors to deliver a specific fertilizer rate for a specific irrigation system flow rate. And then once those are matched, if the irrigation system flow rate changes, then the injection rate changes proportionally. We have a completely separate video demonstrating how to calibrate injectors, and so that won't be covered here in this video set right here. So there are advantages and disadvantages to using proportional fertigation. First of all, in terms of advantages, you don't have to change the chemical flow rates or injection rates when the irrigation sets are changed. And just about every time you change a set on drip or sprinkler, you change the flow rate because there are different number of emitters or sprinklers going on. So there's some specific problems that are eliminated, and such as corrosion. Remember, corrosion occurs when you're injecting high rates of chemicals, and proportional, more or less by definition, it's implied anyway that you're spoon feeding. Incompatibilities, same thing. If you have low concentrations, you don't have precipitation problems. And then we have really strange rules that people use when they put in large dosages. They charge up the system first and wait, that's the quarter of the time. So there's a quarter, half quarter rule, and then half the time they fertigate, and then half the time they let everything flesh out. And yeah, that's important if you have very high flow rates and they don't go out there evenly at first. But really, if you just inject all the time, the fertilizer goes out just as evenly as your water. And so you don't have to worry about all these travel times and unevenness problems. And then you have some specific cases like pivots where they go around and end gun comes on and special units go out to get the corners, and that changes the flow rate, of course, and then you would like to automatically change the fertilizer injection rate. There are more details in chapter 4 regarding this that you can read. Now we get into different types of proportional injectors. For many years we've had these mechanical proportional injectors, and they've been typically used in greenhouses where there's small flows, homes, and small gardens, things like that. They don't have any PLCs or programmable logic controllers. They're just strictly mechanical, and what you have is all of the water goes through the units, and then it's just a mechanism. There's gears or there's pistons, something like that. And for example, if 1 gallon goes through, this piston may make a quarter of a movement or something like that. So and then the piston on completion of a cycle will inject 1 slug of chemical. Usually these things have high pressure losses and low flow rates, and so again they're not typically used on large systems. You can always find exceptions to anything, but it's not usually worthwhile to overpressurize a system. By the way, the pressure is very expensive to develop in terms of horsepower and that, so we usually don't do that. These might be used on systems that are already pressurized. Now, here's where we get into the more recent things. The electronic, as opposed to electrical. Electronic means that there are sensors, that type of thing. Some kind of little PLC or programmable logic controller. And anyway, there are these electronic proportional injection systems, and there are all types of them, and we'll show you a few variations. And some are real complex, some are real accurate, some aren't. A lot depends on the little components that they happen to use. They can be expensive, but here are the basic ingredients for a system like this. First of all, there has to be measurement of water flow. In other words, there has to be a flow meter, and it has to have an electronic output, 4 to 20 milliamps, or a pulse indicator. That there's a wire then that goes and feeds into a controller. You also have to have some way to directly measure or estimate, and usually it's estimation, the chemical flow rate. And then there has to be the injector itself. And then you have a process controller, and you might consider that to be a mini computer. And these things are typically high quality. They're not just chintzy things. So usually you need industrial grade that can handle the temperatures that we see in the dirt and stuff like that. And you have to protect them. And then there has to be some type of an interface. There's a screen, a little touch screen, or there's actually a panel with little pictures on it. And there has to be some way to input the numbers that you want, like the target flow rates or target parts per million. So that interacts with the process controller. So let's start with the irrigation flow meters. What you see here in the forefront on this picture is an old propeller meter. It was a micrometer meter, and if you flip the lid on the top, that gray lid on the top, you could actually read the flow rate and accumulated volume, but there's a little device that's sandwiched in, and you can see a conduit coming out, and what that's doing is providing a pulse indication in addition, and that's going to a process controller. So you can buy these with or without the visual display, and this is just an old example. You can still buy these, and there's nothing wrong with them. So you need that output. The second thing is you need to be accurate. This particular picture is of one that it should be quite accurate. In other words, there's a large propeller inside a spool, that blue spool. It's made at the factory that way. It's a full bore propeller meter. It probably has straightening vanes in it, and it has a nice straight section coming in from the left-hand side here, and it's probably fairly accurate. And I don't recommend insert meters. These are little cheap ones that you put in. You drill a hole or tap a coupler or something like that on the side of the pipe, and they extend into the pipe, maybe an inch or something like that. The thing is they only measure the velocity in a small portion of the flow stream, and you really have to have really straight pipe sections and even flow for them to be accurate. If you do use a mag meter, we call them mag meters or magnetic meters, you really ought to inject downstream of it, because for some of the brands, it turns out that when you have an irrigation mag meter, they get errors in their readings if you are injecting the chemicals upstream of it. So you want to do it. You can check with the manufacturer, but we've seen major problems with that. And just so you know, some of the new mag meters and electronic meters are very accurate, and they can be installed without any straight pipe sections upstream or downstream. So that enables you to squeeze them into a tight situation. So again, this is not a new idea. This image is 30 years old and shows this proportional system, multiple injectors with a propeller meter using a pulsed output. Now, this is where it's hard to keep track of what's going on, and you really have to refer to the chapter in the book. But there are 3 ways to adjust the chemical flow rate with a process controller. One is what you do is you have a chemical pump and a motor, and you change the speed of the motor. In other words, it's a variable speed drive, and that could be alternating current or DC current. So this is where you have a pump, and the pump rotation speed changes. And there are kind of some subsets to this. One is you could say, well, we've calibrated this pump, and we know that at this speed, there's a certain injection rate. And in these conditions, in other words, with this kind of pressure. Or you could have an electronic chemical flow meter. Now this is different. This is not the irrigation flow meter. This is a flow meter for each one of your chemical lines. And it could be downstream or upstream, actually, of the injection pump. And that feeds back to a process controller, which then changes the motor speed. So these are 2 fairly common ways. This idea of using an electronic chemical flow meter is relatively new. In other words, it's new probably, people started to do that in about 2015 or so. They started really using those devices. There's a term here in this particular slide of a VFD, variable frequency drive. Just so you know, a motor in the United States, a standard motor hooked to alternating current, has the current coming into it from the utility at 60 hertz or 60 cycles per second. And so when we talk about a motor speed, for example, 3,600 RPM, something like that, that's a function of two things. It's a function of how the motor is built and that's 60 hertz. And the thing is if you change the hertz, in other words, if you were somehow able to change the frequency of the electrical pulse from 50 to 60, that motor will spin at a ratio of 50/60ths of what it did before. In other words, if you change the frequency by half, you'll change the speed by half. So what we have is we have processors that take the electrical current and change it to direct current and back to some fake alternating current at the speed that we want. And that's all built in sometimes into some of the pumps, or there's a separate VFD controller on the side. This little yellow pump is one you can buy that, just an example, it has it built right into it. And so you can automatically change the speed of the pump with some logic in it. So this is a small pump. They've been around for years and years. The variable frequency drive attributes are relatively recent, but it's a small pump. You can see it sitting on a small tank of some special chemical, some polymer or something that's being injected into a drip system, not a large fertilizer tank. So the first way to adjust the chemical flow rate was to change the speed of the pump. There's another way to do it, and you're probably familiar with pumps, and that is this pump is just spinning along, and you have a valve on the discharge side, and you can change the opening of that valve, and that'll change the flow rate going out. So this is a picture right here of such a valve that's automated. In other words, it would have wires going into it, and it's some controller, some process controller gives it the instruction to open or close somewhat, not completely. And you could either calibrate the valve, you could calibrate the valve and say that we know that at a certain opening there'll be a certain flow rate, or you could use a flow meter downstream and say, the flow's a little too high, and so what it will do, instead of changing the speed of the pump, it will change this opening of the valve. It'll signal this blue black box to move the valve position, and therefore it'll change the injection rate. And this is what we call a feedback loop. Of course, it's an automatic feedback loop where you measure the chemical flow. That information is fed to a processor. The processor says, okay, valve, open or close a little bit. I think that you shouldn't worry about calibrating these valves. It's too much of a hassle. It's difficult to get them just right. Just get a good chemical flow meter. Of course, everything's going to cost money, but that's the way to really do it. There is a third way that's used by some manufacturers to adjust the chemical flow rate, and this is one where it's relatively simple in concept, and it's not always so simple in practice, but it's simple in concept. It says, hey, look at this valve on the chemical line is always going to be either fully open or fully closed. So it's pulsed. In other words, if you want 50% of the maximum flow rate, this thing goes on, off, on, off, on, off. In other words, 50% of the time it's closed, and 50% of the time it's open. It's really relatively simple. And then, if you want a third of the flow rate, it's off, on, off, on. I'm sure you get the idea here. It's a little bit difficult, however, to measure the chemical flow rate when you have this pulsing flow, just so you know. So if you put a chemical flow meter downstream, an electronic chemical flow meter, this pulsing action makes it a bit difficult to get a good reading. So let's go through this thing on process controllers, what they do. The controller somehow gets a signal from the irrigation system, one or more, but it certainly gets the flow rate from the irrigation system flow meter. It has to do that. Then there has to be someone who programs things for each chemical. And so that means that, you know, you can either have well, there are choices here. You can either have an interface which is fairly complex and accounts for all kinds of fertilizer mixes, or someone has to know, have a table and say, okay, I'm going to do AN20, so it's this and that and all that, and here's the rate that I need. So somehow you have to program it, though, for each one of your injectors, what kind of ratio you want. And the next thing is then the process controller is going to somehow change the injection rate. And remember, I gave you 3 different ways that it's done. One is you vary the speed of the pump. Another one is you change a valve opening. And then another one is you do pulsing of the pump, on, off, with a certain percentage of the time. So what I'm really telling you here is that the ease of use, so you buy a fancy controller, the ease of use is going to be highly dependent on the user interface. In other words, what you see, the buttons you have to push. And this is a major weakness for some of the commercial packages. You know, they have good equipment and that, but they're just not user friendly. And the fact is, most people really don't understand much about chemistry. So that's something you definitely look at when you're making a selection. Okay, so this is process control type number 1, where the chemical pump speed is changed, usually with a positive displacement type pump system. So you see the irrigation water going in the big pipe. That's supposed to be the big pipe. And then coming in from the left-hand side is irrigation water, and there's a flow meter up there, upstream of the chemical injection point. And then you go a little bit more to the right, and there's this injection port. Remember, that's where you have a check valve. All the details aren't shown here. You're trying to put the chemical in the middle of the pipeline, that sort of stuff. And that mixes with the irrigation water, and out the other end goes irrigation water plus chemical. So the dashed lines there, starting with the irrigation flow meter on the left, indicate that the process controller is reading the irrigation flow. In this particular case. And so the process controller then tells a VFD controller, which is either inside the pump or it's a separate thing. It says, okay, operate at 75% speed, something like that. That in turn causes the positive displacement electric pump to change its speed. So take a look at this. There are 2 controllers here. One is the one that has the brains in terms of, and that's the one you program. You have this interface with, and it's knowing the flow rate, and it tells the VFD what to do. Nobody gets into the VFD thing. That's just something that kind of comes with the package on these small systems. But it just lets you know that it doesn't happen magically. So what you have is a chemical tank then. The chemical goes into the electric pump. The pump has the correct speed, and it injects the chemical. This image doesn't show any measurement of the chemical flow rate. It's just giving you a general idea of how things are controlled. There's no feedback here in this picture of the chemical flow rate itself. For example, this is more typical of if you had pre-calibrated the pump, and so that you know at this speed it's injecting at a certain rate. There's another type, number 2, that you can buy, And this uses a Venturi. So let's look at this again here, this particular one. Again, irrigation water comes in on the bottom left, goes through a flow meter, a process controller reads it. Okay. Then the downstream of it, water goes, and see, this is different now. Water is being extracted from the irrigation pipe because the Venturis need water as their motive flow. In other words, you have to run water through a Venturi at a high velocity to create a vacuum to pull in the chemical. The previous picture only had chemicals. There was a chemical pump. There was not a water pump. If you take a close look at this picture, there is no chemical pump. There's only a water pump. So what they're doing here is they have a pump with a variable speed, and let's say it has is operating at 100% speed. That means it's pumping a large flow rate through the Venturi, which means there's a large suction, which means the chemical is being brought into that little pipeline at its highest possible flow rate. Now, obviously, you can buy big Venturis and little Venturis and so on. And then you have a mix of the water, irrigation water plus the chemical, and it then enters into the irrigation pipeline. And then that mixes with the larger flow, and out it goes. Now, you find preferences for everything, but just so you know, it's a little tricky when you vary the flow rate through a Venturi to get exactly the vacuum that you want. Some people have done a pretty good job of it, but it's a bit tricky to do it. So we'll go on to the next one here. This third type that's used in commercial units also uses the Venturi. And again, there's a flow meter and irrigation line, same thing. And there's a process controller. But notice what this is controlling. The process controller tells a chemical valve to open or close. The small water pump pumps at a constant rate. It pumps at a constant rate, and so there's always a constant pressure loss through the Venturi. So there's a constant amount of suction on it, and this is pretty easy to regulate then. And the automatic valve then, if it was fully open, would give 100% chemical flow rate, and of course it can be closed down to any amount. And so this is the preferred solution by some people. In other words, instead of changing the water pump speed, they change the position of an automatic regulating valve on the chemical line that feeds the chemical into the Venturi. So here are two different commercial units. These both have multiple injectors. The one on the right, if we start with that, you notice it has 4 different chemicals going in, and I'm not going to talk about all the gizmos on it, but there's a red arrow. It's difficult to see, I know, but we wanted to show you sort of what the whole package looks like. But this unit has pulsating valves. In other words, they're on and off for whatever percentage time you want. So that's how that one works. The one on the left also has valves on the chemical lines, but the difference is instead of being on and off, they're modulated. In other words, they're open, like 50% open or 30% open or what. So it's just a different way of restricting the flow of the chemical that's going in. This one shows the process control 3, where you have a regulating valve. And by the way, this is available commercially. This package like this can be purchased. We're staying away from brands as much as we can. Brands keep changing ownership, and they keep changing parts and pieces, and it's the concept you want to look for. This is really, if they have the right units, if they have the right components, this is really a pretty good setup. what you have is you have a Venturi. See, the idea of these Venturis in the small water pump is pretty simple. The pump never sees any chemical, and so the pump doesn't get corroded by any chemical, and that's one of the big advantages of Venturis. The Venturi itself is really inert. You know, they don't get damaged. At least the ones that I'm familiar with don't get damaged by chemicals. So what this little photo shows you here is the addition of one item to one of the previous slides. And this just shows that there's a digital chemical flow measurement device. And sure enough, you can buy these. There are a variety of them that you can buy, different manufacturers. And again, you have to look around because things change over time. But there are a variety of chemical flow measurement devices that you can use that put out an electrical signal. So in this case, the process controller would say, okay, I have 1,000 gallons a minute, let's say. So I want to inject, let's say, a half a gallon a minute of chemical. And what it would do is it would read the actual flow rate of the chemical through the measurement device. And let's say it's a little too high. Then it would tell the automatic regulating valve to just close down a little bit. And it's a real fast, very reliable mechanism. There's really no calibration of anything. With feedback loops, if you don't get the right measurement flow rate, you don't really care about the details of the regulating valve. If you have too high a flow rate, you just keep reducing the valve opening until you get the right flow rate. It's pretty straightforward. The water pump isn't calibrated. The Venturi isn't calibrated. It's this is how you make it a bit more straightforward. You just have to have good components. Another type of control that you can buy is one where you have a water pump instead. Now this is a pump that's operated by some of the irrigation water, as opposed to an electric driven pump. Now these units are made such that the chemicals never touch the drive water for the pumps. And if you notice, sort of in the middle of the page here, it shows exhaust water that powered the hydraulic pumps, and that's just gone. It's now you could always repump it with the irrigation pump if you had an irrigation pump handy there, but it goes to zero pressure, and so you know, it may just dribble down a ditch somewhere. Who knows? That's a separate problem. With this right here, what you have is again a process controller, and in this case, and it's just that the pumps, if you take a close look at it, and this is in your book, you know, the individual pumps have pilot valves, and you can change the speed at which they're driving through a signal coming in from a process controller. And so if you don't have electricity nearby, much electricity, you could do this. The process controller, though, still takes still requires electricity of some type. They can usually be run by DC power. We have lots and lots of automation of much bigger units on that are automated with solar panel. That's a hassle in itself, but it's certainly very doable. If you notice in this picture, it shows that the process controller is measuring the EC or the pH. That's just as an example. To really get a better handle on this, you sort of have to go through the book a little slower and take a look at the schematics. And then when you examine various pumps that you might purchase, you might have the book with you and try to understand exactly what you're getting. And what you want to look at is what are the moving parts, how accurate are they, what kind of warranty they have, and that sort of thing. A lot of things sound good, but sometimes they're a little complex. And then also make sure you really understand, okay, who's going to actually operate this thing? What will their instructions be? Can they actually manipulate the screen or whatever you're going to have? So this is a different, completely different level than what some people do for very good reasons. They just empty a tank, you know, and they might empty a small tank every day or something like that. That's dirt simple, and everything has advantages and disadvantages. This, just so you know, there are companies who set these things up for you, and I've mentioned this before, they will actually operate these things and service them. And that's just another option that you have.